Hello everybody, welcome into another lesson. So today we are going to talk about finding real zeros of a polynomial function. And when we refer to polynomial functions, I'm going to be referring to third degree and even higher than that. I think everyone by now has a good grasp on finding linear equation zeros. Everyone by now should be able to find quadratic function zeros. So now we're going to get into degree 3 and higher for finding polynomial zeros. And this also will probably seem like a review from Algebra 2. But first thing I want to talk about today is Descartes' rule of signs, which also may seem like a review from Algebra 2. Let's say we have the function f of x equals 2x to the fourth minus x to the third plus 6x squared minus x plus 5. So the goal of Descartes' rule of signs is not to find the zeros themselves. We're not doing that just yet. Descartes' rule of signs will tell you how many positive real zeros you could be looking at and how many negative real zeros you could be looking at. And, what was I going to say? So it'll tell you the nature of your solution. And yeah, I was going to say this is only for real zeros. It does not tell you about complex zeros or imaginary zeros, which a couple lessons from now we will get into complex numbers. We'll review those again and get back to imaginary numbers. But for right now, we're only concerned about real zeros. So if you look at the original f of x, you take f of positive x, which is what f of x is. Descartes' rule of signs says that the number of sign changes you have between each term is equal to that number of sign change or 2 less than that number of sign change of positive real zeros you have. So from 2x to the fourth to negative x to the third, you have 1 sign change. From negative x to the third to positive 6x squared, you have another sign change. And then from positive 6x squared to negative x, you have another sign change. And then from negative x to positive 5, you have another sign change. Okay, so you can count 4 changes of sign. So that means that there are either going to be 4 or 2 positive real zeros. So what this is saying here is the number of sign changes you have, or 2 less than that, for your positive real zeros. Now let's say we came up with only 1 sign change. What would happen then? You're definitely not going to have negative 1 sign changes, negative 1 real zeros. It would just be 1 positive real zero. You wouldn't subtract anything if you just got 1. Now, to find the number of negative real zeros, what you have to do is take f of negative x, which at this point is going to give you 2x to the fourth plus x to the third plus 6x squared plus x plus 5. And if you look at f of negative x, every single term is positive. So in this case, there are no negative real zeros. So Descartes' rule of signs will only tell you the nature of the real zeros you have, how many possible real zeros you have. It doesn't tell you what your zeros are, but that's coming up later this lesson, finding real zeros. So for positive real zeros, you have either 4 or 2 positive real zeros, and you have no negative real zeros because there's not a single sign change in f of negative x. I got 3 more examples of Descartes' rule of signs. All right, so we have here f of x equals 3x to the fourth plus 5x to the third minus 6x squared plus 8x minus 3. All right, so f of x equals 3x to the fourth plus 5x cubed minus 6x squared plus 8x minus 3. So let's look at each term. Since we're just starting with f of x, we're going for the positive real zeros. Between 3x to the fourth and 5x to the third, both these terms are positive, so you have no sign change here. You don't have one. But between 5x to the third and negative 6x squared, you have one sign change. And then between negative 6x squared and positive 8x, you have yet another sign change. And then between 8x and negative 3, you have yet another sign change. So you count 3 sign changes of f of positive x, so you'll have either 3 or 1 positive real zero. And then we have to take f of negative x to try to determine the number of possible negative real zeros. So f of negative x, that's going to give you 3x to the fourth minus 5x to the third minus 6x squared minus 8x minus 3. So if you look at the entire f of negative x equation, you only see one sign change between 3x to the fourth and negative 5x to the third. So what does that mean? You only have one negative real zero. That's the best you could hope for. So for this particular function, you're going to end up having either 3 or 1 positive real zero and 1 negative real zero. 2 more examples of Descartes' rule of signs. Then we'll go on to the rational zero test. This is a good one. All right, g of x equals 4x to the third minus 5x plus 8. So g of x equals 4x to the third minus 5x plus 8. Notice we have no x squared term. And that's okay. For Descartes' rule of signs, we don't need to worry about that. We only take what we literally have here. So since we're taking g of positive x, let's count the number of sign changes. So between 4x to the third and negative 5x, you have one sign change. Between negative 5x and positive 8, you have another sign change. So that means you have either 2 or 0 positive real zeros. So you'll have either 2 or 0 positive real zeros. Now we got to take g of negative x to determine the number of possible negative real zeros. So take g of negative x, you'll get negative 4x to the third plus 5x plus 8. Look at this equation. Between negative 4x to the third and positive 5x, you have one sign change, and that's all you have. So there's only one negative real zero that's possible. So for this particular function, you have either 2 or 0 positive real zeros and just one negative real zero that's possible. One more function for Descartes' rule of signs, and then we're going to go on to the rational zero test. All right. G of x equals 2x to the third minus 4x squared minus 5. So g of x equals 2x to the third minus 4x squared minus 5. Look at this original equation to determine the number of positive real zeros. The only sign change you see is between positive 2x to the third and negative 4x squared. You only have one sign change, so that means you have only one positive real zero. Next thing you have to do is take g of negative x to try to determine the number of negative real zeros. So g of negative x would be negative 2x to the third minus 4x squared minus 5. And if you look at g of negative x, every single term is negative. You have no sign change. So that means you have no negative real zeros. So all you have for this function is one positive real zero possible and no negative real zeros possible. Alright, so that's Descartes' rule of signs. That again only tells you the nature of your real zeros. It doesn't tell you what they are. But now we're going to get to what you really came for, which is going to be the rational zero test for polynomial functions. So let's say you have some polynomial function q times x to the n plus, let's do a times x to the n minus 1 plus b times x to the n minus 2, and it just keeps on going and going and going, plus some constant term p. So a typical polynomial function, heck, we'll even do f of x. F of x equals qx to the n plus ax to the n minus 1 plus bx to the n minus 2 plus a constant p. To find the possible real zeros, you take that p, you actually take plus and minus p over plus and minus q. So you're going to take the positive and negative factors of your constant term divided by the positive and negative factors of your leading coefficient, and the fractions you get will be your possible real zeros. So let's go ahead and try to solve some of these. Well, actually, they could all, possible real zeros, but we'll show you here. So let's do an easier one. So f of x equals x to the third plus x squared minus 4x minus 4. And actually, to be honest, we could solve this by factoring by grouping, but I don't quite want to do that right now. I want to show you how the rational zeros test works. So first thing you want to do, that 4 is your p, that coefficient of 1, your leading coefficient, is your q. So let's take plus and minus p over q. So positive and negative factors of 4, you have plus and minus 1, plus and minus 2, and then plus and minus 4. Over positive and negative q, positive and negative factors of 1 are just that, plus and minus 1. So that means in the end, your possible rational zeros are plus and minus 1, plus and minus 2, and plus and minus 4. Alright, so what you got to do now, once you found your rational zeros, your possible rational zeros, you have to use synthetic division to figure out which one's going to work the best. So synthetic division, unfortunately, is a lot of trial and error, but that's the way it's done. So let's set up some synthetic division here for this polynomial. So x to the third coefficient is 1, x to the second coefficient is 1, x to the first is negative 4, constant term would actually also happen to be negative 4. I'm going to use positive 2. Let's take positive 2 as a possible rational zero. So now let's go ahead and bring down that 1. So what's 2 times 1? That's going to be 2. Well, 1 plus 2 is 3. 2 times 3 is 6. Now negative 4 plus 6 is 2. All right, 2 times 2 is 4. So negative 4 plus 4 is 0. By the factor theorem, x minus 2 is a factor of this polynomial. So now what you need to do is take this f of x, write it in its factored form. So that 2 really stands for x minus 2. So f of x would equal x minus 2 times the quantity of, that 1 is a coefficient now of x squared. It's 1 less than your original polynomial. So x minus 2 times x squared plus 3x plus 2. And yet we can factor this a little bit further, can't we? We can definitely factor this further. That quadratic factor will factor. And since we're trying to find all the rational zeros, then we need to factor this completely. So this will turn into the quantity of x minus 2. Now x squared plus 3x plus 2 will factor into x plus 2 times x plus 1. So now you have a completely factored polynomial, which you have 3 factors. So you take all 3 factors, set them equal to 0. In the end, you should get that x equals both plus and minus 2 as well as negative 1. So x equals both plus and minus 2 and negative 1 for your 3 solutions. And the degree of your equation, again, tells you the maximum number of solutions you could possibly have. So some of those solutions could end up being imaginary solutions. It just happened to work out that all 3 of them were real. And today we're only concerned with the real solutions. But at some point, we will be doing complex solutions. We'll get into the fundamental theorem of algebra, which will talk about complex solutions of a polynomial equation. All right. Minor change here. So f of z equals z to the 4th minus z to the 3rd minus 2z minus 4. So we have f of z equals z to the 4th minus z to the 3rd minus 2z minus 4. So first thing you want to do is find your possible rational zeros. So take your plus and minus p over plus and minus q. Well, your p is, again, your constant term. So factors of 4, that's going to be plus and minus 1, plus and minus 2, and then plus and minus 4. All over your q, which is your leading coefficient, in this case is 1, that's just plus and minus 1. So your factors are going to end up being plus and minus, or your possible rational zeros, plus and minus 1, plus and minus 2, and then plus and minus 4. Okay. So then once again, we have to use synthetic division to figure out which one of these rational zeros are actually going to work. So let's go ahead here. Let's do our rational division. Let's do our synthetic division. So the z to the 4th term has a coefficient of 1. Z to the 3rd is negative 1. We don't have a z squared, so we have to put 0 for that coefficient. Z to the 1st is negative 2. And then the constant term is negative 4. All right. let's do... Why don't we try -2? And again, this could be a bit of trial and error. If you don't get it your first time, that's okay. You're allowed to do trial and error. So bring down that 1 from above. Now -2 times 1 is -2. So -1 minus 2 is -3. -2 times -3 is actually +6. All right, so 0 plus 6 is 6. All right, -2 times 6, that's -12. -2 minus 12 is -14. -2 times -14 is 28, and then -4 plus 28 is +24. We have a remainder of 24, which means that x plus 2 is definitely not a factor of this polynomial, or z plus 2, I should say. So we're back to square one. We need to try again. Let's try +2. All right, so let's do +2 this time. So let's see, bring down your 1. Okay, what's 2 times 1? Well, that's just going to be 2. -1 plus 2 is +1. 2 times 1 is 2. All right, 0 plus 2 is going to end up being 2. 2 times 2, that's going to be 4. -2 plus 4 is +2. And then 2 times 2 is 4. Well, -4 plus 4 is 0. So it looks like that 2 is the rational 0 that fits. What does that mean? That means now we have f of x equals your factor of, or f of z, excuse me. I'm so used to working with x, but f of z would equal the quantity of z minus 2. Now, that coefficient of 1 is the coefficient of 1 less degree than the leading coefficient of the original polynomial. So this would be z to the third plus z squared plus 2z plus 2. And we can definitely factor the cubic factor further. That's just a matter of simple factoring by grouping. So this is going to turn into z minus 2. Let's make a bracket here. That's z squared and z cubed. You could factor out a common z squared times z plus 1. Then with 2z and 2, you could factor out a common 2. That would be times z plus 1, which would make this factor further into z minus 2 times z plus 1 times z squared plus 2. And now we know we can't factor z squared plus 2 any further. If you try, you'll have two imaginary roots. So the only ones we really got to consider are z minus 2 and z plus 1. That means z equals +2 and -1. And yes, we have two imaginary solutions, that's true, but today we're only concerned about the real zeros. So z equals 2 and -1. Now there will be problems, unfortunately, where you may have to do the rational zero test and use synthetic division multiple times. You will sometimes have that, so just a heads up. Alright, so what do we got this time? F of x equals 4x to the fourth minus 55x squared minus 45x plus 36. So this looks a little bit hideous, but that's okay. So first thing again, let's come up with the possible rational zeros. So plus and minus p over plus and minus q. So that p again is your constant term. So factors of 36, you have plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4, plus and minus 6, plus and minus 9, plus and minus 12, plus and minus 18, and then plus and minus 36. All over your factors of q, which is your leading coefficient, in this case 4, factors of 4 are plus and minus 1, plus and minus 2, and then plus and minus 4. So that means your possible rational zeros are going to be plus and minus 1, plus and minus 1/2, plus and minus 1/4, plus and minus 2, plus and minus 3, plus and minus 3/2, plus and minus 3/4, plus and minus 6, plus and minus 9, plus and minus 9/2, plus and minus 9/4, plus and minus 12. All right, so let's see. That's 9. That'd be 9/2. All right, we're good there. So 18. So let's see. You'd also have plus and minus 18. Let's see. Yep, that's 9. All right. Then you would have plus and minus 36. And that's it. That's all you would have. So you have a lot of possible rational zeros. So let the games begin for finding out which one is going to work. So let's do the synthetic division here. So your leading coefficient of the polynomial is 4 on the x to the 4th term. You don't have an x to the 3rd, so that coefficient is 0 by default. The x squared coefficient is negative 55. The x to the 1st coefficient is negative 45. The constant term is going to be 36. Now we do synthetic division to figure out which possible factor works. And this is going to be a bit of a doozy. Why don't we start with, well, let's start any place. Let's start with 1. It may take a while to go through some of these, but when in doubt, start at 1. So bring down your first number of 4. 1 times 4 is what? Well, that's just going to be 4. 0 plus 4 is 4. All right, 1 times 4 again is 4. Now negative 55 plus 4 is negative 51. Okay, 1 times negative 51 is negative 51. Negative 45 plus negative 51 is negative 96. 1 times negative 96 is negative 96. And then 36 plus negative 96 is negative 60. Well, you have a remainder of negative 60, so clearly positive 1's not going to work. Let's try negative 1 and hope that works. Alright, let's just throw a negative sign on that 1 and see what happens. So bring down your 4 again. So, alright, negative 1 times 4 is negative 4. Alright, so 0 plus negative 4 is negative 4. Negative 1 times negative 4 is positive 4. Okay. Negative 55 plus 4 is negative 51. Negative 1 times negative 51, that's positive 51. Alright, so negative 45 plus 51, that's positive 6. Now negative 1 times 6 is negative 6. 36 minus 6 is 30. Darn. So that means we have a remainder of 30. Well, negative 1 isn't a factor. So now we've tried both 1s. We can probably go ahead and erase that from our list so we don't keep coming back to it. Okay, let's go with positive 1/2. Let's try to divide by positive 1/2. So bring down your 4. Alright, so now what is half of 4? That's just going to be 2. 0 plus 2 is 2. Half of 2 is 1. Negative 55 plus 1 is going to end up being negative 54. Alright, half of negative 54 is negative 27. Negative 45 plus negative 27 is negative 72. Uh-oh, what happens? Half of negative 72 is negative 36. Well, 36 minus 36 is 0. So actually, we found our factor. We totally found our factor. So let's put this function in factored form. This would mean f of x equals the quantity of x minus 1/2 times the quantity of 4x to the third plus 2x squared minus 54x minus 72. Well, what I'm going to suggest here is we factor out the common 2. We can at least start there. So f of x would end up equaling 2 times x minus 1/2 times 2x cubed plus x squared minus 27x minus 36. Well, we have it a little bit better factored. Just a little bit better. But it's not going to be as easy as factoring by grouping. So unfortunately, we're going to have to do this all over again. Unfortunately. So what I'm about to do now is I'm going to rewrite all this up top because I'll run out of room on the board if I don't. Oops. So let's see. That means f of x equals, you can distribute that 2 inside the x minus 1/2. You would actually get the quantity of 2x minus 1. Then this would be times 2x to the third plus x squared minus 27x minus 36. No, you know what? The more I think about this, let's not distribute that 2. Because we're going to ultimately need to find the factors anyway and solve for all the zeros. So there you go. Let's go ahead once again find our rational zeros. So take your plus and minus p over your plus and minus q. Well, your p is your constant term, so that's going to be factors of 36. So again, plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4, plus and minus 6, plus and minus 9, plus and minus 12, plus and minus 18, plus and minus 36. All over factors of q, which is your leading coefficient. In this case is 2. Factors of 2 are just plus and minus 1, plus and minus 2. So we're not going to have as many rational zeros, but we still will have some. This would give you a total set of rational zeros of plus and minus 1, plus and minus 1/2, plus and minus 2, plus and minus 3, plus and minus 3/2, plus and minus 4, plus and minus 6, plus and minus 9, plus and minus 9/2, plus and minus 12, plus and minus 18, and then plus and minus 36. Those are all your possible rational zeros. So not quite as many, but still a lot. So now let's go ahead and set up our synthetic division. This time we're doing the synthetic division for that cubic factor. So the x cubed term has a coefficient of 2, x squared has a coefficient of 1, x to the first has a coefficient of negative 27, the constant term is negative 36. All right. Let's start at 1 again. Let's divide all this by 1. So bring down your 2. 1 times 2 is in fact 2. 1 plus 2 is 3. 1 times 3 is going to be 3. Now negative 27 plus 3 is negative 24. 1 times negative 24 is in fact going to end up being negative 24. Negative 36 minus 24 is negative 60. We get a remainder of negative 60, so positive 1 doesn't work, unfortunately. All right, let's try negative 1. Again, it is a bit of trial and error sometimes. So bring down your positive 2. Negative 1 times 2 is actually negative 2. All right, 1 minus 2 is negative 1. Negative 1 times negative 1 is positive 1. Negative 27 plus 1 is negative 26. Negative 1 times negative 26 is 26. Negative 36 plus 26 is negative 10. You have a remainder of negative 10, which means that's also not a possible solution. So we can get rid of those plus and minus 1s. Let's work on 1/2. So let's do, whoops, I probably better erase what's here, right? So let's see here. Plus and minus, let's do plus 1/2 first. So bring down your 2. All right, so half of 2 is 1. 1 plus 1 is 2. Again, half of 2 is 1. Negative 27 plus 1 is negative 26. Half of negative 26 is negative 13. Negative 36 minus 13 is negative 49. That remainder of negative 49 means half isn't a factor. So let's try negative 1/2. All right, so bring down your 2. Negative half of 2 is negative 1. 1 minus 1 is 0. Negative 1/2 of 0 is 0. All right, negative 27 plus 0 is negative 27. Negative half times negative 27, that's positive 27/2. So this would be the same as negative 72/2 plus 27/2. That would end up being negative 45/2, which a remainder of negative 45/2 means it's definitely not a factor. So none of your plus or minus 1/2 are acceptable factors. Let's now try for 2. Alright, so let's try 2 as a rational zero, and what I mean by that is positive 2. So bring down the 2 from over here. 2 times 2 is 4. 1 plus 4 is 5. 2 times 5 is 10. All right, negative 27 plus 10 is negative 17. 2 times negative 17 is negative 34. Well, negative 36 plus negative 34 ends up being negative 70. You have a remainder of negative 70. That definitely doesn't work. Let's try negative 2 as a possible rational zero. So bring down your 2. So negative 2 times 2 is negative 4. 1 minus 4 is negative 3. Negative 2 times negative 3 is positive 6. Negative 27 plus 6 is actually going to be negative 21. Negative 2 times negative 21, well, that's positive 42. Negative 36 plus 42 gives you 6. So that remainder of 6 doesn't work. That means your plus and minus 2 are eliminated as possibilities. Let's go on to 3. And again, sometimes you may have to be here a while doing trial and error, unless you know off the top of your head which one works, and sometimes that's hard. Let's go ahead and try plus 3. All right, bring down your 2. So 3 times 2, that's 6. 1 plus 6 is 7. 3 times 7, that's going to be 21. Negative 27 plus 21 is negative 6. 3 times negative 6 is negative 18. Negative 36 minus 18 is negative 54. You get a remainder of negative 54. That doesn't work, so let's try negative 3. All right, so bring down your 2. Negative 3 times 2 is negative 6. 1 minus 6, that's going to end up being negative 5. Negative 3 times negative 5 is positive 15. Negative 27 plus 15, that's negative 12. Negative 3 times negative 12 is positive 36. Well, would you look at that? Negative 36 plus 36 is 0. That means that we found a factor. So we can write this factored again for the function. You'll have f of x equals 2 times the quantity of x minus 1/2 times now that x plus 3. And then you'll have 2x squared minus 5x minus 12. Let's see if we can factor this quadratic and get a complete set of solutions. Well, obviously 1 and 2 are factors of 2. You have 1 and 12, 2 and 6, 3 and 4. I think we actually found it. So that'd be 8, that'd be 3. So I'm pretty sure this is going to factor into f of x equals 2 times x minus 1/2 times x plus 3 times x, and then you have a 2x. So let's see, 2 goes to 4, and then this goes to 3. So 2x squared plus 3x minus 8x, that's the minus 5x, there's the minus 12. All right. So we factored this completely now into f of x equals 2 times the quantity of x minus 1/2 times x plus 3 times x minus 4 times 2x plus 3. Set each of these factors equal to 0, you get that x equals 1/2, negative 3, positive 4, and then negative 3/2. So in this case, all 4 of your solutions were real solutions. Since it's a 4th degree equation, you should have 4 solutions. definitely in the complex numbers. In this case, all four numbers happen to be real. You get x equals 1/2, -3, 4, and -3/2. There is a simple x to the 5th function I'd like to do. It's not nearly as grueling as this one. Not nearly as grueling. You're not going to have nearly as many possible rational zeros. Not even close. Let's do a x to the 5th function. So f of x for sure equals x to the 5th minus x to the 4th minus 3x to the 3rd plus 5x squared minus 2x. Well, what do we notice right away? What do we notice right away? You don't have a constant term. Your p is your constant term. So, but we didn't even need that because you have an x in every single term, right? We can factor out x right away. You end up getting x times x to the 4th minus x to the 3rd minus 3x squared plus 5x minus 2. All right. So we factored out our x. Now we're down to a 4th degree factor, which is a little bit better. Now we need to find the possible rational zeros of the 4th degree factor. So take your plus and minus p over q. So your p is your constant term of -2. Factors of that are simply plus and minus 1, plus and minus 2. Over your factors of the leading coefficient of x to the 4th, just plus and minus 1. So your possible rational zeros in this particular case are going to be plus and minus 1, plus and minus 2. Now let's do synthetic division. So you'll end up getting, let's see, coefficient of x to the 4th is 1, coefficient of x to the 3rd is -1, coefficient of x to the 2nd is -3, coefficient of x to the 1st is +5, constant term is -2. All right. Let's try +1 first as a rational zero. So go on ahead, bring down your 1 from above. Now 1 times 1 is 1. -1 plus 1 is 0. 1 times 0 is actually 0. -3 plus 0, that's -3. 1 times -3 is -3. So 5 minus 3, that's going to end up being 2. 1 times 2 is 2. -2 plus 2 is 0. You have a remainder of 0, which means that 1 is the rational zero that works. So this is going to factor into f of x equals x times that x minus 1, now times x to the 3rd plus 0x squared, so we'll go right to minus 3x plus 2. So now we got it down to a cubic factor. Good news is we can keep the same rational zeros for the cubic factor. Why don't we go ahead and give those a try? Let me write up here what we got now. We have f of x equals x times x minus 1 times x to the 3rd minus 3x plus 2. All right, let's go ahead and do that synthetic division again. So coefficient of x to the 3rd is 1. X squared, you have a coefficient of 0. X to the 1st is -3. Constant term is +2. So why don't we try 1 again? So let's go ahead and bring down that 1. 1 times 1 is 1. 0 plus 1 is also 1. 1 times 1 is 1. Negative 3 plus 1 is negative 2. 1 times negative 2 is negative 2. Well, 2 minus 2 is 0. So that means x minus 1 is yet again a factor. So the very next thing that just happened here is we have another factor. So f of x equals x times x minus 1 times another x minus 1. Now this becomes quadratic times x squared plus x minus 2. Well, we can simplify those two x minus 1s. We can write that as x minus 1 to the second. So this would equal x times x minus 1 to the second power times, let's take the factors of x squared plus x minus 2. You should end up getting the quantity of x plus 2 times x minus 1. X squared minus x plus 2x is plus x minus 2. Good, okay. Which could simplify one more time into x times x minus 1 to the third times x plus 2. That's the best we can do. So it looks like we only have 3 zeros. But here's the thing. That x minus 1 to the third, that's technically 3 of your zeros. Then you have 1 at x plus 2 and then 1 at just x. So that's still 5 zeros as far as this is concerned. It's just the 1 0 has a multiplicity of 3, which the next lesson we're going to get into graphing polynomial functions, and we'll talk about what the multiplicities mean as far as graphing behavior goes. So now you just set each factor equal to 0. So you'll literally get x equals 0, x equals 1, and then x equals negative 2. But that 1 has a multiplicity of 3. But you only have to write it one time. So x equals 0, 1, and negative 2. Those are all your solutions to this 5th degree polynomial. So that's it for this lesson. Next lesson, we're going to graph polynomial functions. So I hope everyone has a great day. Take care.